Hi everybody, today's lesson is about the trends of the periodic table. So we're continuing with your notes. We did periodic table A for the arrangement, and now we're on B for trends. So you already know that a group goes down and a period goes across. So we're going to talk about trends like as you go down a group, what things change, and as you go across, what things change. So first thing we're going to talk about is radius. So atomic radius is the distance from the nucleus out to the valence electrons. So how is that distance different as you are looking, first of all, down a group? So this one is the most obvious. As you go down a group, there's one orbital, and then two, and then three, and then four, and it keeps going. Each period tells you the number of orbitals. So obviously its width is increasing. So as you go down a group, the atomic radius increases. So here I have an example for you. In period 1 is hydrogen with just a single ring, and its atomic radius is 32. Period 2 is lithium, 2 rings or 2 energy levels, 2 orbitals. Its atomic radius is 130. And in period 3, sodium, so these are all group 1, but they each have one more orbital, so their radius is increasing for each one. All right, the next one. This one you wouldn't maybe expect. This one sometimes surprises people. As you go across a period, it gets smaller. And so I want you to think about why it would get smaller. First of all, you know the number of rings aren't changing. So what does change as you go from element 3 to 4 to 5 to 6 to 7 to 8? What changes is the number of protons in the nucleus, and those protons are what draw the electrons closer. So the more protons you have with the same number of orbitals, it helps draw that orbital in closer, and therefore the valence electrons are closer, and therefore the radius is decreasing. So as you go across a radius, as you go across a period, the radius decreases, electrons are in the same orbital, but more protons in each nucleus pulls the electrons closer. All right, I also have a visual for this one. So I am going, I have 2 atoms that are both in period 3, sodium and chlorine. You'll notice they both have 3 rings. They're both in period 3. But the distance is much further out for sodium than chlorine. And the difference is right here in the protons. So 11 protons do not pull the electrons in as much as 17 protons do. So the radius goes from 160 down to 100. All right, next trend is called electronegativity, and I love to do this with my fingers. Electronegativity is the ability of an atom to attract electrons to it. So the nucleus is the positive mama nucleus, and it's just drawing those electrons towards it. So we got to talk about who's good at being electronegative and who's terrible. So first thing I want you to think about is size. The bigger an atom gets, the worse it's going to be at electronegativity because the nucleus is too far from the valence electrons to attract others in. So the first one's going to make a lot of sense to you. As you go down a group, electronegativity decreases. Each orbital makes the nucleus further away from another atom's valence electrons, so it's harder to attract those electrons to it. And here's an example. Period 2, period 3, and period 5. These are all group 16. So this has 2 rings. It has a really high electronegativity because it's easy to draw them in. It's close to the nucleus. When you get down here to sulfur, harder to draw them in, and technetium, only a 2.1. All right, the next one, as you go across a period, the electronegativity increases because electrons are now closer to the nucleus and they're in the same orbital. So again, it's because there's those protons able to pull them in. The radius is smaller, so they're able to attract those electrons better. So here I give you an example. Across period 2, we've got lithium far on the left in group 1, and fluorine is actually the highest on the electronegativity scale. It's in group 17. It's a halogen. And I want you to be thinking about, why didn't I pick a noble gas? Did you think of the answer? Noble gases don't want to have electronegativity. They don't want to attract electrons. Remember, they're perfect. I'm a noble gas. So lithium, wide radius, not as good at drawing in electrons as fluorine. So here are their values. Lithium's electronegativity is a 1.0 and fluorine is a 4.0. Fluorine has the highest electronegativity of any element on the periodic table. All right, next one, ionization energy. So I like to use props for this. Ionization energy is how much energy would it require to remove my outermost valence electron. So if I am an atom and I'm holding my electron way out here, it's going to be easy for you to take it away from me. So my ionization energy would be really low. If instead I have a small radius and I don't want to lose any of my electrons, I want to gain them, I would have a high ionization energy. So it would be hard to take this away from me. It would have a lot of energy required to do that. All right, so as you go down a group, ionization energy decreases, of course, because I've got more rings, it's further away from me. It's much easier to get an electron away from me if I have this really big radius. Think of it, you could think of it like the mom goes to the store with her kids, the grocery store, and if her radius is really large, meaning that the kids are further away from her, it's easier to lose a child. Whereas if the kids are on those, remember those little, they almost look like little chains that like the kids are backpacked onto. If she holds her children really close to her, she's not likely to lose a kid. So her ionization energy is really high because they're staying right close to her. So as you go down a group, ionization energy decreases. Each orbital makes the nucleus further away from the valence, so it's easier to remove a valence electron. All right, and I have some examples of that. Period 1, period 2, period 3, these are all group 1. Each one has less and less ionization energy. So it's very difficult to get an electron away from hydrogen. Its ionization energy is very high. It's easier to get an electron away from sodium because its ionization energy is lower. All right, now, as you go across a period, I want you to now be thinking to yourself like, oh, I know what this one's going to be. So as you go across, of course, the electronegativity increases because they're holding their electrons so close and the positive nucleus is really attracting them in. So to lose one of those electrons would be difficult. So electronegativity goes up as you go across a period. All right, I have some examples here. Period 2, again, I have lithium and fluorine, and we already talked about that fluorine has the highest electronegativity. It also has the highest ionization energy, which means it has those 7 valence electrons held very tightly, and you're not going to be able to take any of them away. Whereas lithium just has 1 valence, and it's sort of like, oh, yes, take this. So it has a larger radius, easier to remove its outer electron, much more difficult to remove this one's outer electron. All right, the rest of the notes are going to be quite easy because we've already talked about them. So the first one, metal character. Where is the most metal? The left side losers. And the more able it is to lose an electron, the more metallic it is. So if you think of the periodic table, you want to go all the way to the left side and down. The ones with the big radius that have very few valence electrons are the best metals. They lose their electrons easiest. Losing an electron is called oxidation. They oxidize really easily. So metallic character, most metallic properties, those are our left side losers, means they have things like conductivity, luster, malleability. So as you go down a group, that metal character increases because big radius, easy to lose electrons. All right. As you go across the period, the metal character goes down. It's not a left side loser anymore. You're going to the right. So on the right side, it's all about the non-metals. So as you go across, metal character decreases because electrons aren't lost as easily. All right. Next one here, non-metal character. So this is the opposite, except for remember, I don't want to include those noble gases, but the most non-metallic properties is all about gaining electrons. So as you go down a group, it is becoming less and less and less like a non-metal. It's becoming more like a metal. So as you go down a group, that character decreases. And as you go across, the non-metallic character is going to increase because they hold their electrons close. They have a small radius. They are much more likely to gain electrons than they are to lose. All right, so I have a periodic table here on the next slide, and I want you to just think about each of these trends. And I have one filled in that I will leave on the screen for a second for you to copy through, or you can pause. But as you think about the periodic table, I want you to remember as you go down a group. So here I am going down group 1. What things happen as you go down a group? First of all, it's becoming more like a metal. So metal character increases as you go down a group. That's because the radius is getting bigger and it's more likely to lose an electron. Its ionization energy is going down as well, which means it's really easy to take an electron away from Fr right here, francium, compared to any of the other metals in this group. So again, as you go down, the radius increases. The electronegativity, the ability to draw those electrons in, goes down. The ability to take an electron away goes down. It's easy. The energy required to take it away, very little. All right, now, as you go across, what things are changing? As you go across, it's becoming more like a nonmetal, so it's more likely to gain electrons. That tells us the radius is getting smaller, it's better able to attract electrons in, and the ionization energy is very high, meaning it's hard to take electrons away from them. So this last slide, you're going to want to pause the screen and you're going to want to write these things down. So as you go from the circle to the arrow, it's showing what happens. So the radius as you go down, this is showing that is where it increases the most. So wherever the arrow is, that is where it is the highest. Wherever the circle is, that's where it's the lowest. So the radius increases as you go down. The radius decreases as you go across, which is why over here the small radius is going to be on the right side of the periodic table, and the largest radius is over here. The metals, you want to go down to the left side. The biggest metals on the left side loser are the most metallic behavior. Non-metallic behavior is just the opposite. Your fluorine is going to be your best nonmetal. That's why it has the highest electronegativity and the highest ionization energy. Both of those increase as you go across because it is first of all able to draw electrons in, and it's not able to lose electrons easily. It holds on to those electrons. And then over here, electronegativity is the lowest at the bottom with big atoms. Think because the nucleus is too far away to attract electrons in. It's the best with the small atoms. That's why the top of the arrow is up here. Ionization energy, low down here. The bigger it is, the easier it is to take an electron away. Whereas when they're small, up here it's going to be the highest ionization energy because it's hard to lose those electrons. So again, if you want to pause it and spend a little bit more time writing this down in your book, and if you want to write it differently than what I have, like ionization energy increases, fine. Make sure if you have any questions, you ask me tomorrow in class. Thanks.